So, as you see in my title, today we're going to talk about deep learning and machine learning in R. So by now, we all have seen this Venn diagram, right? You have to have this by our very own Drew Conway, the original progenitor of the R meetup. And it's like a rule. You need to show this at a data science meetup. Right? There's even data science bingo. And this is one of the slots that you need to fill. But there's rumblings of a new Venn diagram. This comes from the deep learning book. And what it says is that AI is this encompassing field, and that machine learning is a subset of that. And within machine learning, you have deep learning. Now, some people say that deep learning is its own thing, not comparable to the rest of machine learning. Other people will just say it's one technique of machine learning. So we're going to dive into both of those for a little bit. But first, when you're getting into them, you need to learn about them. So we need some good books. And there's plenty of good books in both fields. On the theoretical side, you have The Elements of Statistical Learning by Hasty, Tibshani, and Friedman. Then you have Deep Learning, right to the point, by Goodfellow, Bengio, and Corville. Now, these are both math books. They're heavy on math, heavy on theory. If you want to learn how to do the code, we have Applied Predictive Modeling by Max. Where are you, Max? Right there. And Deep Learning with R by J.J. Allaire. Where's J.J.? J.J.'s somewhere. There he is. Now, these books are just code. So if you wanted to learn the theory, first read the other two books. You want to learn code, read these two books. Highly recommend all four of them. They're really, really good reads. Take it with you when you go to the beach. Excellent for that. Now, the two disciplines have the same things, but different words. For some reason, there's been a massive split in the terminology used between machine learning and deep learning. And it can be infuriating, right? So let's see some examples of that. First up, we have linear regression, because that solves the majority of your problems. So first up, and it looks like we do not have internet for my slide, so my latex math is gone. Oh no, the latex math is there. I just don't have it on my screen. Wonderful. Y equals A plus BX. Simple linear regression. We've all seen this. I hope we've all seen this. If you haven't seen it in terms of statistics, this is slope-intercept form from middle school. Right? We've had it A and B. But those terms have very different words depending what field you're in. Machine learning calls it an intercept. Deep learning calls it a bias. Then the B term, what comes after that? Machine learning calls it coefficients, whereas deep learning calls them weights. Well, that's a problem, because in statistics, a bias is something completely different in the bias-variance trade-off. Huge important concept. And weights in statistics are how much you value each row. So they're completely reusing terms, not just a new term, they're reusing a term. And that could be very difficult to get your head around. Then we have this curve. It is generically a binary scaling curve, right? We all know the math behind this. It's 1 over 1 plus e to the negative x, right? Well, depending on your field, it's either an inverse logit or a sigmoid. We needed a new word for it because inverse logit just didn't sound cool. Then we have L2 penalization. Incredibly important, shows up in a lot of algorithms, and beyond machine learning and statistics, it shows up everywhere. This is essentially the sum of the squares of the terms. Very important penalty. It's the L2 norm, the squared L2 norm, actually. And in machine learning, that's a ridge, and in deep learning, it's weight decay. And then when it comes time when you have new data and you're trying to score your new data, well, that is, in mathematical terms, y hat equals f hat of x tilde. In machine learning, that's prediction. And in deep learning, that's inference. But that word is really problematic. So you're using it for prediction here. But in statistics, inference means explanation. You're actually explaining things. And the first time I heard people talking about using inference for prediction, I'm like, that's just wrong. But throughout history, there's been lots of terms for the same thing, and you just got to learn when to use which one, depending on your crowd. So let's get into some R code. That's what we're all here for today. The examples we're going to be looking at are supervised learning. Y is a function of x. That's majority what people do. And particularly, we are going to look at binary classification. Because let's be honest, 90% of the time when someone has AI, they're doing a logistic regression. So let's take a look at this. Let's first look at machine learning, traditional ML. And we're going to focus on today just two algorithms, GlimNet and XGBoost. Probably two of the most important, powerful algorithms in machine learning. For either one, the first thing we have to do is set up our matrices. So when you're using LM or GLM, you can just put in your formula and the data frame, it all works nicely. You can't do that with these algorithms. You need to provide the matrices in numeric format ahead of time. Fortunately, in the useful package, there's a function called build.x that will build it for you in build.y. You give it the formula like you would have for a regular model, you give it your data frame, and in this case, I am saying contrast equals false. This way we don't drop the baseline of categorical variables. And sparse equals true to have a sparse matrix, because sparse matrices take up less space and they compute faster. I'm using the credit data, so it's a nice small data set, tiny data, that everyone's familiar with. Now, while I use build.x for this, it is theoretically possible to use the recipes package, but the functionality I wanted wasn't ready yet by the time I wrote this, but Max has promised me it's on GitHub already. It is. Thank you, Max. Just a little too late for me. So let's talk about the elastic net, which is a combination of L1 and L2 penalization. And that's implemented in GlimNet by Hasty, Tibshirani, and Friedman. And the really cool thing about that package is it's actually written in 73 lines of Fortran. That's it. And everyone here, a lot of people know that Fortran's a verbose language, and they somehow did that. It's amazing what they did. So let's fit our first model. With one line of code, we not only fit a penalized regression, we did cross-validation over the lambda. We fed it the x, we fed it the y, told it it's a binomial regression and do 10 folds. In one line of code, we got all of that done. Nice, simple, easy. And when we're done with that, we can visualize the coefficient path using coefpath. If you're used to using the GlimNet package, you could plot the model, but it's static, it's hard to see. So I use digraphs to build coefpath, which now has it interactively. You could zoom in, you can hover and see what's happening. And as you read this, you could see that as your lambda, your penalty increases, the coefficients shrink towards 0, and eventually get to 0, and that's your minimization. Nice, quick, easy visualization. Let's say you have one value of lambda, and you want to see the point estimates for your coefficients. You can use coefplot, tell it you want to use lambda.min, and it very quickly shows you the point estimates for each of your coefficients. Much better than a table of numbers out to like 5 decimal places. You can very quickly and easily see the impact of each individual coefficient. Now, of course, if you're using a regular linear model, you would have confidence intervals. But penalized regression doesn't give you confidence intervals. But who cares about that anyway these days? No one seems to care about confidence intervals. Right? It's machine learning. You're making a prediction that's going to last 5 seconds, so you don't care anymore. But maybe you should. So that is penalized regression. The next algorithm I want to talk about are decision trees. And despite their name of decision tree, they actually do both regression and classification. They're called decision trees not because of the outcome variable, but it's because of a series of decisions as you split up the input variables. And while there's lots of ways you can do this, we're going to skip straight to XGBoost because it's just like the most awesome thing put out there in machine learning recently. Before we actually fit the model, we're going to take one more data step. We're going to create a special object, an xgb.dmatrix, which stores the x and y variables in one object for you to keep them together. And we're doing that both for our training data and our validation data. But notice this. They call the x matrix data and the y matrix label. Regression was clearly an afterthought when they were building this. Right? Otherwise, they would have called it x and y, or predictor and response, or input and output. They were clearly thinking about classification. But now that we have our data ready, let's fit the model with one line of code. Sure, I broke it up on multiple lines so it fit on the screen, but it's just one line of code. You give it that special data set. You tell it you want to use GB tree. And that's cool, because if you switch it to GB linear, it's going to fit an ElasticNet. XGBoost can fit penalized regression models. But we're going to stick to the tree. You tell it it's a logistic model. I do 500 rounds. I set early stopping. I give it validation data. And I get a nice model. And what's really cool is this works on a GPU. Now, boosted trees are sequential. But when you're searching for the split in each of the trees, that could be in parallel. And you could do it on a GPU, and it could be incredibly fast. Even faster than XGBoost already is. And you can even have an experimental concept here where you could do a boosted random forest. So that's really awesome. You can fit multiple trees in parallel and then boost those groups of parallel trees. When you're done with this, you get a variable importance plot. And you can very quickly see which variables were important in the fitting. Not the impact of the variables, but the importance of them. And if you want to try to visualize all 500 trees in one, you can. It does its best to compress 500 trees into one tree and show you representative splits. Is this understandable in the slightest? No. But it's a good first effort, and we will applaud them for that. But in case you want it to be even simpler, we can use the Karis package. This provides a uniform interface in R for all of the machine learning needs. It's incredibly simple, and it's been around for over a decade. This is the original AutoML. They couldn't ask for anything better than this. So there's two models I just fit. Each one can be done in a single line of code if you have a formula, a data frame. And the only difference between these two snippets of code are the method. One is glimnet, one is XGB tree. So thank you, Max, for making it so easy. So that's machine learning very quickly. Next, we have deep learning. And everyone's excited about deep learning now, right? It's all the rage. But I think a better name for it is extreme nonlinear modeling. Because that's where you're getting the power from. It's the nonlinearities. It's the activation functions that give you the nonlinearities. And that's where the real strength is. That's why XGBoost works so well. It's capturing nonlinear relationships. The two primary ways of doing this in R are MXNet and Karis. MXNet is championed by Amazon, and Karis and TensorFlow by Google. There's a slight issue. You can't have both of them loaded in the same R session, but JJ Lair's promised a fix for me. I'm taking that as a promise. Now, we could do other neural networks in R. NNet by Brian Ripley has been around for decades, but it can only do single layer. You could also do CNTK, DeepNet, RNN, DARCH, RCPP, DL. There's no shortage of deep learning in R. Despite what people say, there's many packages to do it in R. So first, let's rebuild our matrices. Same as before, but we can't use sparse matrices, because neither MXNet nor Karis/TensorFlow can handle sparse matrices. That's OK, though, because we're going to have large data. We can use iterators and generators to load them into memory a little bit at a time, because they use stochastic gradient descent. They don't need all of the data. So first, let's look at MXNet. This was, for a while, the primary way to do it in R. It's portable to Windows, Linux, Android, Raspberry Pi, and it's CPU or GPU. This is an MXNet model, a simple MXNet model. We first do a layer dropout to prevent overfitting. We have a fully connected layer, which is a dense layer. All the inputs are connected to all of the temporary in-between nodes. We use a ReLU activation function. We do dropout. Then we do another fully connected layer with another round of dropout and another ReLU, until we get to our last layer, which is just 1 because it's binary and it's 1 or 0. And we have an output, a logistic regression output. And that's the sigmoid output, or the inverse logit. But we're not ready yet. We need helper functions. We first need to write our own custom log loss function, because there's not one built in. So we use log loss because that's better than binary loss. And if you want to keep track of your results, you need to create a logger to keep track of your metrics as you go. So now that we build that, we can go fit the model. So first, you need to feed it your x and y matrices. You tell it the optimizer you want. I chose Atom for adaptive momentum. You give it your evaluation data to see how you're going. I'm doing this on a CPU. I'm choosing to use log loss as my metric. I'm doing 50 passes through the data. I set my learning rate. I set my batch size. I tell it how the data is set up. I have a callback to check my metrics. And then I'd say verbose, and I could run this. A lot of options you need to set just right. So then we get the outcome of this, and we can plot it using digraphs. And we can see how we're doing over time. Clearly, this data set's not appropriate for deep learning. It's a very messy thing. Our loss function's all over the place. But you get the idea. You can see how you're doing. And our data set definitely needs to train for much longer if we want to keep doing this. Well, let's see the new kid in town. Let's check out Karis. This is a port of Karis, thanks to J.J. Allaire and Francois Chollet. And by default, it uses TensorFlow as a backend. It's primarily meant for Linux, but it does work on Mac and on Windows. And you can use a GPU, mostly on Linux. I've tried a few ways to hack it into Windows, but it's mostly on Linux. So let's design our network. This is a similar network to before, but using Karis notation. In our first layer, which is called a layer dense now, we tell it we want 512 nodes. And instead of specifying the activation layer separately, we specify it right in the layer dense function. And for your first layer, you need to tell it the input shape, which if you take your dimensions, you forget the one that's about the number of samples, it's the number of features. And if you have multi-dimensional tensors, you have to give a few of these. But for our data set, we just tell it the number of columns. We then do batch normalization to help with the fit. We do dropout. Then we do another dense layer, another batch normalization, another dropout. And we do a sigmoid output. But after we set up the network, we then have to compile it. We set the optimizer to be Atom again. And this time our loss function is binary cross entropy, which is the same thing as log loss, but we needed a new word. We use accuracy as our metric. And notice here, you're not saving this back to an object. It's not like traditional R. You're modifying the variable in place. So net Karis has now been modified by calling compile on it, and it is a different object now. It's been changed. It's been mutated. So it's very important to note it's a little different than standard R. So now that we've compiled it, we can go ahead and train our model. We tell it the number of epochs, the batch size we want, our validation data again, and then we say callbacks. Because you can't just say early stopping. You need a callback that at the end of each epoch, it says, hey, should I stop? You need a callback for showing us your metrics. You need a callback for changing your learning rate. You need a callback for TensorBoard. So after you've gone and trained the model, this time only on 10 epochs, you can, once again, see how you're doing over time and compare your training and validation set. Clearly, our model needs a lot of work. We need to train it more, and we need to maybe use different data set. But that's the goal behind this. Not every data set is suited for deep learning. So wrapping up, what's the big picture of this? Well, you could use centuries-old terms, or you could use brand new terms. For machine learning, there are many, many, many packages. Carrot has 238 algorithms you could choose from. Deep learning, there's about 7. But deep learning's only been around for a few years, so it is a very, very good start. Machine learning, for the most part, you could do it in one line of code. But in deep learning, it takes many, many lines of code. So you have to know what you're doing. It's more verbose. In machine learning, we have Carrot. Thank goodness. In deep learning, there is Carrot, but it can only do simple networks. It can't really do extreme deep networks. It can do simple networks. Machine learning, you might get some explanation out of your models if you're doing a linear model, and maybe a single tree decision tree. Deep learning, it's just for predictions. Now, machine learning will already give you strong predictions, and deep learning might give you better predictions. But when it does better, it does really better. It really does better. Now, where they're both the same, they both have some really, really great books out there, like I showed you earlier. I highly recommend all of those. And both fields still have a ton of excitement about it. And that everyone is very deeply excited about all of these. So thank you very much.